Hello and welcome again as we look at yet another multiple choice question for IB Chemistry. Which property explains why tetramethylsilane, TMS, SiCH3,4 can be used as a reference standard in hydrogen-1 nuclear magnetic resonance NMR spectroscopy? What is tetramethylsilane and why it's used as a reference standard in this technique, which is used to identify an unknown chemical substance based on certain structural properties? Now, the NMR spectroscopy machine measures data concerning hydrogen atoms. When you use a molecule like tetramethylsilane, CH3, which is 4 times 4 of these attached to silicon, like this, CH3, silicon here, 4 CH3s attached to it. What you have, of course, is a molecule that's very stable with no dipole, because you have what's known as the inductive effect from each of these methyl groups being exactly the same, pushing electrons towards this silicon. This molecule, of course, is very symmetrical, it's non-polar, and there's very little intermolecular bonding between one molecule of TMS and another one. And once you have that situation, you would expect boiling point in this structure to be quite low, because the bonding between one molecule and another would not be as strong, with no significant dipoles and definitely with no hydrogen bonding. So therefore, it's not going to have a high boiling point. So you can eliminate this. It's not going to be a reactive compound either. What you have is a structure that is very much along the lines of the very unreactive alkanes. All you have really is a silicon where a carbon would have been. And this, of course, is a completely saturated structure, and there are no oxygens or nitrogens or anything. So it's not going to be a very reactive compound at all. And all of the protons, all of the hydrogens, are in the same chemical environment. Now, what does that mean? That means that each hydrogen is in a place where the atoms around it influence it the same. So this carbon with its 3 hydrogens here, and this carbon with its 3 hydrogens, and this one, and this one, for all of them, the hydrogens are in identical chemical environments. That, of course, opposed to a structure like this, where these hydrogens in CH3OH are all in the same chemical environment, but this one here attached to the oxygen is in a completely different chemical environment. And what NMR spectroscopy does is that it's able to identify hydrogens based upon the chemical environment that they're in. So if they're all in the same environment, they're all going to give one signal on the NMR spectroscopy machine, and that's exactly what happens with TMS. It gives a signal for 12 hydrogens all downfield at the lowest possible level, and that's used as the baseline in the NMR machine, giving it a chemical shift value of 0. So this is what makes TMS very good. It's got 12 hydrogens to give you a big signal, all of the hydrogens in one spot on the NMR spectrum. It doesn't have a high boiling point, so it's easy to get it out of the machine when you're done. And of course, it's not reactive, so it's not going to have any remnants in there reacting with other substances that go into the machine as well. And it doesn't give multiple signals, of course, like I said. It only gives that one signal, which is used as the 0 point on an NMR spectrum. The answer for this question, of course, C.